I am posting these. I haven't put them up to the playlist recently, but they're up. The videos are up somewhere. Okay, so chapter 5 is about stereochemistry. And stereochemistry has to do with three-dimensional shapes. So you're probably going to need a model kit for some of this, so I put it out, but don't grab it yet. We'll need it in a little bit. Okay, so three-dimensional structures of molecules can greatly affect its physical and chemical properties. All right, so can you give some examples where three-dimensional shapes matter? And they're being real vague here. I just like this idea of the slide. But you know that if you compared the boiling point of that, and these are constitutional isomers of each other, they're going to have really different properties, right? The one on the right has the hydrogen bonding. The one on the left doesn't have hydrogen bonding. So you know that three-dimensional structures of molecules can make a difference. So constitutional isomers, for example. It turns out also, though, the three-dimensional shape, how molecules are spatially arranged, matters, even if they have the same formulas and same constitution. Constitution simply refers to how the atoms are connected to each other. So molecules with the same constitution can have different effects. A good example, and this is one I just pulled from the literature, is based on adrenaline. So what do we use adrenaline for? Biology people, come on now. Yeah, the flights, right? Or fight, right? Or when you scare people, because Halloween's coming up, someone's going to jump out from behind somebody and scare you, and that adrenaline is going to make your heart rate increase. It's going to do vasodilation. You'll be able to inhale and get more out of the air, right? Your heart rate increases so you can run or fight, right? Or a bunch of other things. Well, adrenaline is this molecule here, and you'll notice the way that the molecule is drawn is that it has a group. That's our internet. Stop using it. I'm using the school's internet instead of my own little wireless system because I was having problems with that too. Every once in a while, I'll be talking and pointing, and you won't see a pointer, and then about 20 seconds later, you'll see this pointer go, and then it'll be done, and then it'll be caught up. So this OH group is coming out towards the front, okay? This molecule has stereochemistry, and I'll explain that to you simply like this for now. This OH group can either be in the front or it can be in the back. And it turns out those are two different molecules. Now, this is known as the Pharmacophore. It's the model, okay, molecule that albuterol is based on. So albuterol is something that a lot of people in Central Valley use because, I mean, we have a lot of asthma, we have bad air, all that good stuff. Albuterol is shown on the bottom left. Now you notice how I drew this molecule, right? By the way, right, you see there's not much modification. This group's different. This one, you notice I didn't put a hatch or a wedge on it. When it was originally synthesized, because remember, albuterol is based off of this, right? When this was originally synthesized, they couldn't make it with one group in the front and one group in the back. You ended up with a mixture of some of it, half of the molecules had the group in the front, half the molecules had the group in the back. So this mixture is actually what they're administering to people, okay? Oh, sorry, my bad. This is albuterol here, and that's what. And so I drew it like this. Oh, sorry. There's an enzyme that does this, but let me get back to this part. So that's what this wedge is here. So this is albuterol. They added an extra carbon here. Okay. They put what kind of group is this? T-butyl group onto here. Okay. It has some of the same effects as adrenaline does, but not all the same effects. But it has, in particular, what we like is it has that bronchial dilator effect. Causes the little sacs that absorb oxygen to dilate. Okay, so The reason that they made this modification, actually, and I totally blanked, I forgot about this. There's an enzyme called catechol O-methyltransferase. This is a catechol group. And this is how adrenaline is, one of the ways adrenaline is deactivated and then metabolized. And so to prevent this from happening, what they did is they just added an extra carbon here, and it has still has some of the same pharmacological effects as the adrenaline does. Okay, so here's the story, though, right? They were able to eventually make pure, this is called the R version, and I'll explain to you how we get the R version, and pure S version, and then they decided to test both of them in a study to look at how this has what effect this has on people when they administer it this way. Now, it turns out this S-albuterol apparently doesn't affect everyone, but 36% fewer hospitalizations by simply making the pure R-albuterol. Okay? So you think about, multiply that times the thousands and thousands and thousands of people that go in for asthma attacks and get treated with albuterol and respiration therapy and all that kind of stuff. That's a lot of people that could be affected by this. Okay. Turns out albuterol, though, I think, if I'm not mistaken, is still a mixture when it's administered because it doesn't have that big of an effect on everyone. Okay. But anyways, the shape of the molecule, by putting this group in the front versus in the back versus having this group in the front, has this big of an effect. So the question is, why does that happen? It happens because in your body, these molecules interact with receptors, right? Now, receptors are actually physical objects. So they have places where parts of the molecule will attach themselves, okay? And when they attach, they activate usually some sort of ion channel that then creates a response in the cell. If the shape, if you just take two of those objects, right? Think about this molecule, and I'm going to build this on a small scale. And I'm going to use nice colored spheres so you can see this. Let's say this is one of the albuterols, right? And it has this shape, and this is the receptor, and it's sitting on the cell wall. And then the albuterol comes in and makes contact. In order to fit into the shape, the green one has to be here, the purple one has to be here, and the black one has to be here. This is the rest of the molecule, right? That's activation, okay? If you take it and you switch it like this, and that comes in, it doesn't fit anymore. Because this part of the molecule has a different shape, and this part of the molecule has a different shape. And when it comes in to activate the receptor, it can't. And in fact, in a lot of times, in these kinds of receptors, one shape has one effect, and another shape has a different effect. So like when you smell, let's see, what do we call it commonly, caraway or spearmint, it turns out that's the same molecule with two parts switched. And they smell dramatically different. If you smelled caraway is rye bread, and spearmint is like gum, right? Generically. It's not wintergreen, but it's spearmint. It has a shape, and I hate wintergreen. If you get one shape in your nose, like think about this going up in my nose, right? It's like, oh, I smell like caraway, and then if I switch these, right? And I stick it up my nose, then it goes to another receptor, and that's when I smell mint. Okay? So it's the shape of the molecule that's really important. This whole area that we're about to study is called stereochemistry. Stereochemistry implying that the shape of the molecule is important, and we need to understand how molecules are shaped in order to understand their chemistry and to understand the effects that the molecules have. And that's the book picture. So I'll skip it. Oh, by the way, that's an amino acid, right? Amino acids have to fit into a receptor in order for the whole transcription process, right? I said that backwards, I guess, but anyways. For that whole process, the molecules have to have the right shape. All the amino acids have a particular shape to them, so they fit in a receptor and work through the machinery that we have. in our bodies produce proteins. If it's the wrong shape, it doesn't work. Okay, so isomers. Isomers are non-identical molecules that have the same formula. So we talked about constitutional isomers already. Those are just same formula, but different connection of atoms. Constitution is different. Stereoisomers, same formula, same constitution, spatial arrangement is different. Okay, so pair of molecules that are constitutional isomers. I already did that on the first slide, so skip it. Here is an example of a stereoisomer. This is kind of the simplest stereoisomer that we can have in a lot of ways. It's a cyclohexane, right? It's got two methyl groups. There's two methyl groups in the front, right, on both molecules. That means the constitution is the same. They're connected the same way. But you notice that one of the CH3s is down, right? So these two molecules have the same connectivity but are actually different molecules, and then have different properties. Okay? Yeah, so we call this one cis. Cis just means together, trans means apart. Okay? And if you, when you get into the naming of these things, trans is actually referring to the hydrogens being apart from each other, or the hydrogens being together. If you replace one of those hydrogens with a chlorine, there's no good way to say cis and trans, because you're like, well, cis of what, trans of what? Which groups are together, which groups are apart? Turns out there's a set of rules that we use, okay? And we'll be able to do cis and trans that way. And you'll see. Maybe not as always as clear, but you'll see there's other naming systems. So I make a point, if there's one hydrogen on each substituted carbon, then cis and trans notation can be used. Totally acceptable. Okay? So this molecule at the bottom, as far as nomenclature goes, right? This is cis 1,2-dimethyl cyclohexane, right? Because you would have named this dimethyl cyclohexane. 1,2-dimethyl cyclohexane. This one is trans 1,2-dimethyl cyclohexane. Excuse me. Okay, why do we have a cis and a trans in this case? For example, let me try this on you. Taking them apart. Did no damage. So this molecule, right? This is supposed to be butane. I don't have all the hydrogens on there, and one of them is red. Just pretend it's butane. Okay. Why can't I call this cis, and why can't I call this trans? Because I can call that cis and trans. Why don't I call this cis and trans? Why don't I say this is trans and this is cis? I just showed you the answer, but go ahead.
I was going to say, when you turn it that way, the hydrogens are still the same direction?
No. It's simpler than that. It's because the molecules rotate. Like, when you say, oh, that's this, you might be able to say that, oh, these are together, and there's actually a term for that that's related to cis, but you could say these two are together. But it doesn't really matter, because at room temperature, this molecule is just rotating around. It really is the same molecule. But on a ring, right, the ring can't rotate. So when you make that molecule with the CH3s going up or the CH3s going opposite directions, right, those CH3s are fixed in place. So one of the ways that we talk about you're able to have cis and trans is when you have a restriction in the ability to rotate, okay? So you have this constraint in rings, and you also have it when you have pi bonds, because remember, if I had put a double bond in the middle of this big molecule, put a pi bond in between here, then it doesn't rotate freely, and as a result, I can have cis and trans again, okay? Constraint, yeah, and the constraints typically are you have a ring So it can't rotate, because you can't rotate one half of a ring. You have to rotate the whole thing, right? And when you have pi bonds. Yeah. I just rewrote these slides. I think I like them. How long have I been doing this? Yeah. Hours and hours and hours. Every time I do it, I'm like, oh no, it could be better. Sorry, OCD. And I did finally start grading labs, so you should start getting those back soon. Sorry. I always tell myself, I'm going to be good. I'm going to grade the first 4 or 5 labs that come in and get them back to them. And then I start reading them, and I go, oh, these are horrible. Sorry, no offense, guys. I'll just read the next ones and then full credit for the first ones, and we'll just call it, we'll just all be good with that. Sorry, but they're much better now. Okay, so what we're going to do is identify whether the following pairs are either constitutional isomers, stereoisomers, or identical. Okay. So 1. Identical. It's a ring flip. Ring flip doesn't make a different molecule. Okay. So first one, I'm just put an I here and put an arrow in between. Say ring flip. 2. No, it's not constitutional. Do this, okay? And they're not identical. Okay, so now we have the answer. But we're going to do this. We're going to number the carbons. So we're going to go 1, 2, 3, 4, 5, 6. I'm going to start on it, and I'm going to do the same thing on the other one, right? So 1, 2, 3, 4, 5, 6. And this is as if I was going to name it, but the numbers, even though you don't know how to name an alcohol, we haven't gone over that, even though I haven't heard that stuff yet, you can still number a ring so you can identify whether or not they're constitutional isomers. And you'll notice that I have carbons at all positions, of course, because it's a cyclohexane. And then I have OH groups on 1 and 2. So they're at the very least constitutional isomers. Identical.
Which is a requirement for stereoisomers.
I'm sorry. What's that?
There being constitutional isomers is a requirement.
No. I was just saying at the very least they're constitutional isomers because they have the same stuff, right? Are they identical? That's the next question, okay? And the answer is, well, on carbon number 1, the OH is going up on both. Up being top side of that carbon. Because this carbon has to have, just for example, has to have a substituent that goes down here that's a hydrogen. This one has a substituent over here that's a hydrogen. Okay. What's the number 2 carbon? Well, on one it's going up, and then the other is going down. Okay. So even though it's rotated, right? And the ring is flipped. Actually, it's not rotated, but you could rotate it too. The ring is flipped. You can tell that the groups are not on the same side like they are on the molecule on the left, right? This is the cis molecule. This is the trans molecule. Because they go opposite sides. So they're stereoisomers of each other. Oh, sorry. Let me back up why I did it. I don't even think about these things sometimes. So I numbered it and I counted it to make sure they're constitutional isomers. If they're at the very least they're constitutional isomers, they can be stereoisomers or they can be identical. But if you do the counting of the carbons and you get different numbers, then they can't be any of them. Right? That's just the way my brain is.
Will you be able to say that after you count it and you find out that they're constitutional isomers and there's some formula that since they're not both like axial, like one has axial and an equatorial?
That doesn't matter. Ring flips change that. Yeah.
This doesn't trans only apply to stereoisomers, it can also apply to constitutional isomers.
It's stereo. It's a constitutional. Okay. I'm just trying to think of. I know what it says on the first slide that I showed you, but think about it like this: constitutional isomers, things are connected in a different arrangement. Okay. So stereoisomers are a type of constitutional isomer. That is, they're connected in the same way, but they're spatially different. So because they're spatially different, we tend to just isolate them as stereoisomers. Same connection, right? Constitutional isomers have supposed to have a different constitution. But it depends on how deeply you see constitution. If spatially arranged is a different constitution, then you would say they're constitutional isomers. On that first slide, yeah, right. Same molecular formula and constitution, right? So does that make them constitutional isomers? Well, like here, right, same molecules but different constitutions. So these have the same constitution. So yeah, anyways. Just remember, constitutional isomers should have different formulas. Stereoisomers have different spatial arrangements, same constitution. Now, if your brain is like mine, it says, well, different arrangement is constitution, isn't it? Right. I'm not going to get that picky on the definition. Yeah. Okay, so, back up. Let's do a couple more. E, better number it, right? Just in case. So 1, 2, 3, 4, and 5. And then 1, 2, 3, 4, and 5. So what do you think? Stereo. Because the double bond is in the same place. Okay, watch this. I'm going to make another one. What about those? Those are constitutional isomers. Double bonds in different places. Different connections. So it's a different connection. Okay. So even if I had done this, it would have been constitutional. Oops. Cool. Okay.
And the reason why it's stereo for number 3 is because it went from trans to cis, right?
Yeah, yeah. The way you make that determination, okay, a lot of people have trouble with this. Draw a line here. I've got a hydrogen here. And I got a hydrogen here. The hydrogens are different sides of the line. They're trans. Okay? On this molecule here, if I draw the line like that, through the double bond, okay, and then I add the hydrogens in, they're on the same side of the bond, so it's cis. So a lot of people miss the fact that the line that tells us cis and trans has to be drawn through the double bond. And if you don't draw it through, like along the double bond, then it's hard to tell which is cis and which is trans. Okay, so 4, don't think too hard. Constitutional. You should count the carbons, though, right? And count the oxygens. And then there's an equivalence between the ring and the double bond, so you should know that. So you can identify it as constitutional. What about 5? Same thing. You could draw it like this, if you wanted to draw a line on this one like that. And then you could say there's 2 methyls together on this side, draw a line like this. There's 2 methyls together on this side, so that's right, going to be the same thing. The other thing, though, that you can recognize right away is because these groups are the same. Ooh, what's this do? Ooh, I could do that. Since those groups are the same, Having two of the same groups on one end of the double bond means that it doesn't have a cis or trans. Okay? They're identical groups. All right. So I'm going to skip this slide because I've already covered all that information. And we already did this in the earlier slide, so I'm going to skip this slide. Now, there's another kind of stereoisomer, and this is the one that albuterol is. It's known as a chiral stereoisomer. And chiral comes from the Greek, I believe, maybe Latin, but I think it's the Greek for hand or handedness. Okay, so you could have a left-handed molecule, or you could have a right-handed molecule. Your hands are chiral. That's why we use this term. Right? Take your hands, go like this. Okay, chiral molecules. And go Om. All right. It's a Zen thing. All right. Your hands are mirror images of each other, right? It actually feels pretty good. But when you go like this and you try to superimpose them, they're different. Okay? So these are what are said to be mirror images that are non-superimposable. When I say superimposable, I say superimpossible, but sorry. Superimposable. Non-superimposable simply means when you take the mirror image of your hand, of an object, and try to lay it right on top, it can't. Okay? Your book has all this stuff about your chiral, because your left and right hand sides aren't exactly the same. But a lot of people don't realize your left and right hand sides aren't exactly the same, so it freaks them out. They're like, what? So you can read that stuff in your book if you want. Right, so your hands are not superimposable, they are chiral. Okay? If it is superimposable, then it is not chiral. Okay? Objects, for example, that might be what we say achiral. I'm just looking for things. No, there's small differences. I don't have a good example of a coffee mug. Hang on. Oh yeah, here we go. Well, this one's a little bit more complicated to think about. But you notice how this thing has symmetry to it? Like down the center, right? Like the left side and the right hand side are the same. If I make the mirror image of this object and then I just line it back up, it'll be the same object. There's no writing, well, there's a little writing on here, just ignore that. There's no writing on here that you can see. So it looks, for all practical purposes, if you took the mirror image of this object, it would look just like this object. It would be superimposable. Anything that has symmetry is what we say achiral. This coffee mug, for example, with mold on the inside, ignoring the mold. Does this belong to any of you? I've been sitting in here for weeks. Right? This coffee mug is achiral because if I take the mirror image of it, right, I could have another coffee mug here and then bring the images together, they would superimpose on top of each other. Okay? So again, non-superimposable mirror image. Molecules that most often exhibit chirality are molecules that have 4 different groups on them. So I'm going to pause this for a second, and I want you to... Okay, so now try this, right? Then you're saying, like, say you make them touch it, too, and then you just fold it together, and you can see, like on mine, the green and white, they're opposites of each other. Now you say to yourself, well, I'm just going to make the green and whites the same. I'm going to just rotate this over like this, and then what happens? The other 2 at the back don't match, right? So no matter what you do, it's like super impossible to get them superimposable. I thought I'd just put that in there. Okay, I don't think superimpossible is a word, though. So now what we're going to do is we're just going to take, just to verify, take just one of you, okay, pull 2 bonds off of one of your molecules and switch their positions. Now try to make the mirror images of each other. in practice, you shouldn't be able to do it. I've had people be able to do it, and I explained to them that they just pulled them off and put them back in the same place, but it does happen. So like I got my greens to match, and my purples are in my fingers, and now my red and orange, right? Or my red and white, sorry, don't line up. So now what you do is, let's see if you can make these things superimpose. Right? Ta-da! I'm holding my red ones, and then my green, purple, and white, they line up, okay? These are the same molecules now, okay? So, switching a pair, okay, of bonds creates the enantiomer. You can switch another pair. It doesn't matter if it's the same ones. Switching another pair, right, gets you back to where you started. It's just a rotation of the same molecule, most likely. Okay? This is going to become important when we draw stereoisomers, that if you can't visualize the stereoisomers, you still have to be able to manipulate them to be able to tell things about them. You need to have some rules about how you can rotate bonds around. And the rules are basically what we just covered. Switch two pairs, switch two bonds, right? And switch another two bonds. It doesn't matter which two, okay? And you'll be back to the same molecule. So how do you switch bonds, right? So let me do it on this drawing that we have here. So let's say I wanted to, on this molecule, okay, I want to draw the same molecules, but now with the bonds rotated. And let's say I want the hydrogen to be where the ethyl group is. All right? So what I'm going to do is I'm going to start by drawing my hatch and wedge like this. And I'm going to make it in exactly the same orientation as on the screen. Ooh, that's going to be a very fat wedge. So this is a very detail-oriented thing, which I am horrible at. But I want the hydrogen where the ET is. I want the ET in the front, right? So I'm going to put the hydrogen here. I'm going to put the ET here. Now, if I put the OH and the ME in exactly the same place, I will have actually drawn the molecule on the left. Do you see that? I would have drawn this molecule if I put the OH here and the ME here. The bonds are a little bit like this is still forward from this is forward, and this is back. But it would be exactly the same molecule. That's not my goal in this, though. I just want to redraw this one with the hydrogen in the back. I switched these two groups to get to this position here. If I don't want to draw the stereoisomer of this molecule, that is, the word is enantiomer, what do I have to do? Okay, if I want to draw this molecule simply with a bond rotation, like I switched the H and the ET here, what do I have to do with these two groups? I have to switch them. You always have to switch pairs in the rotation of a molecule, okay? So in other words, I would put the OH down here and the ME at the top. And now what I've done is I've redrawn this molecule, okay? I've redrawn this molecule over here, but I've rotated the bonds in a way that it turns out is going to be easier for me to analyze later. Okay.
It's the same molecule?
It's the same molecule because, and even if you can't see it, you could see it when you had a model kit in your hand, that if you switched two pairs, you got back to the same molecule. And if you didn't see that, do you want to try that? Again, just specifically do this, okay? First, make the same molecule. So you should be there right now, okay? Same molecules. Okay, now, pull one of them, no. Don't pull them both apart. Just take one and switch two atoms. And this is what I want you to do. I want you, now you should have the enantiomer. Switch any two other atoms. You can even switch one of the same atoms that you switched before. So I switched orange and green. Now I'm going to switch green and purple. I didn't even touch the white one. Right? I'm so confident this is going to work. I have not rehearsed this. What did I do? I made the same molecule again. So it doesn't matter which two you switch, as long as you switch two pairs, so total of 4 bonds being switched, you always get back to the same molecule. This is true on models, it's true on paper. I don't rely on any of these tricks. I'm pretty good at visualizing them, so I just kind of look at it. Oh, yeah, that's different. But that's just a whole... You just get there after a while, after you've played with these enough, held models in your hand enough, okay? It'll work out for you. Okay. Chiral molecules are said to have a stereogenic center. If you change two groups, it gives you a different stereoisomer. Okay, so if I have this molecule and it's chiral, and I draw it on paper, and then I switch two groups, and I would end up with the enantiomer of that molecule. That's known as the stereogenic center. You can generate a stereoisomer by switching two groups on the center, which is kind of what we've been exploring right now. Okay, so analyze the attachments for each chiral center below. Okay, and decide what the 4 groups are. So I'm helping you out. I highlighted, or they highlighted, the stereocenter. And then for each one, we will draw its enantiomer. Okay. So on molecule on the far left, what are the 4 groups? Say it slower. Chlorine. This carbon. This ethyl. Now, it's everything attached to that side. So the groups, when we say a chiral molecule most typically has 4 different groups, you have to look at everything attached to it and the order they're attached. Okay? What's the 4th group? Hydrogen. So that would be like this. Now, if you wanted to draw the enantiomer for this, the stereoisomer of this, there's 2 ways you can do it. One, you can literally draw its mirror image. Okay, one is you draw a line like this, and then you draw backwards from the right to the left, if you're artistically challenged like I am. You do that. And that is the enantiomer of that molecule. I just drew the mirror image of it. I know it has 4 different groups on that center that's chiral already, right? So when I do that, that's the enantiomer. The other way to do it, what have we been doing so far? Just switch 2 groups, right? Which 2 groups? Doesn't matter. Yeah, you could switch the ethyl and the methyl, so you could draw it like this, and then draw this the same. Or I could switch the Cl and the H. Or I could switch the H and the ethyl, and I could switch the Cl and the methyl. Right. I mean, I'm not going to do them all, but you guys, from handling the models, get that will give me the stereoisomer, right? Okay. Oh, and you know what's going to happen on test, right? I'm going to give you a bunch of molecules and say, which one of these are stereoisomers and which are identical? And it'll just be the same 4 groups on one center. And there'll be, you know, a half dozen of them. You'll have to go, this switched with that, switched with this. Yeah, anyways. It's a credit, no credit kind of thing. It's hard to, if I asked you to explain it, like for every single one, you'd be like, this switched with this, and this switched with this. These are the same.
If we get model kits, would we be able to use them on the test?
No, model kits are not allowed on the exam. So you have to learn how to do this. Now, I'm going to show you how to do it with your fingers. All right? I don't know. I might relent on it, but no, I've never allowed model kits. Now, Miss Henry, she's so nice. She lets people have model kits, but you should see her exams. They're crazy. Like when you give students a model kit for an exam, you're like, I'm going to build the craziest thing. They're not going to have enough atoms. And they'll be like, oh, God, Mommy. Yes. Actually, my mom knows a lot of chemistry, so I could probably say that, and she'd probably help me. So, by the way, what are the four groups on that central one? The alcohol, the ethyl, and the propyl, and the hydrogen. The hydrogen. And to draw a stereoisomer, I'm just going to switch the hydrogen and the OH. Oops, no, I didn't. That's what I meant to do. But you know, you can switch any of them. And if you don't know for sure, then you could just ask me after you've drawn it. I'll tell you if it is or isn't. Okay, so this is the one that messes people's heads up. Starts to, anyways. I'm telling you that's chiral, right? What are the 4 different groups? Okay. Well, bromine's one. What's the other one that's hydrogen? What are the other 2? The ring going to the right and the ring going to the left. It's the same ring, but you notice how there's a double bond in there? So it makes one side different. So to the point of difference, that's a group, and that's a group. And those groups are different, even though it's the same ring. If I hadn't put the double bond there, then going to the right and going to the left would have been the same, and it actually wouldn't have been chiral. Okay? It's weird to think, but it's a ring, they're connected. Going to the left and right, if the double bond's not there, it's exactly the same. Okay. So let's find the stereocenters here. Let's start with, I'm going to call it, oh, hang on. Yes, there's many on these. So we're going to call this, I want a better color. Ooh, that's a good color. Probably going to look horrible on the screen. We'll call this one A. We'll do this one as B. This one is C. And this one is D. So let's work with A. Oh, it's stereocenters and chiral centers. So how many stereocenters do I have on A? And I'm going to number the parent chain. 1, 2, 3, 4, 5, 6, 7. So let's analyze these. Which carbons have stereocenters? 4 and 5. Okay. What are the 4 groups? Let's do with number 4, right? What are the 4 groups on 4?
That's CH3.
Get back there. Yeah. So the CH3, hydrogen, all of this stuff on the very slow mouse pointer and all of this stuff on the very slow mouse pointer. Right? Okay. So there's those two. Now, Stereocenters includes this trans, right? And if you'll notice this group here, it could either be with the methyl group or on the opposite side of the methyl group. So this double bond, that's also a stereocenter. Because a total of 3 stereocenters in there for that molecule. The two smaller circles are the chiral centers. Okay? Those produce the enantiomers, or there's another term we'll talk about, distereomers. Okay. Okay. So what about B? Where are the stereocenters and what are the 4 groups? Okay. Let me number the ring again for nomenclatures, like we would do for nomenclature. 1, 2, 3, 4, 5, and 6. Where are the stereocenters? Yeah, 1 and 2. Fairly easy to spot. That one, that one. There's a hydrogen here, right? And then there's a hydrogen here. The 4 groups on each are actually the OH, oh my God, the H. Our network's really slow. My thumb has moved way over and it's just, the ring going this way and then the ring going this way. Okay. So you look at the ring, it's different going that way and that way. Right. And for that one, you do the same thing. It's the O, the H, the ring going that way and then the ring going that way. Okay. All right, C, let's number that like we are for nomenclature. 1, 2, 3, 4, 5, 6. Where are my stereocenters? Three and 4. Okay, so how many of you think 2 is a stereocenter? How many think? Right? Honest, be honest. How many think 2 is a stereocenter? 2 is not a stereocenter. It's just drawn like it's a stereocenter. 4 different groups, right? What's this? Methyl. What's that? Methyl. 2 of the groups are the same. So try this. Take your model. Prove this to yourself. Pull off 1 atom of each, the same. So I pulled my purple ones off. And what I'm going to do is I'm going to stick white ones on it. Okay? So now I have 2 whites. All right, now hold one of the white atoms. I'm going too fast. Sorry, I'll help you with that. There you go. Okay, so, right? You got your mirror image, right? Now watch what happens. Superimpose them. You can make the whites line up. Even if they're not lined up, let's say it's like this, right? And your green and your reds are opposites, doesn't really matter because the whites are whites. Same molecule. You have to have 4 different groups. So if you have 2 methyl groups, right, it can't be chiral. It can't be a non-superimposable mirror image. You can make a mirror image, but it's superimposable. Okay. So, yeah, only 3 and 4. I think only 3 and 4. Let me double check. Yeah, only 3 and 4. And D. Well, It's achiral because the ring going in this direction and the ring going in this direction are exactly the same. Okay?
So a stereocenter has 4 different groups, and then chiral center.
No. A chiral center is a stereocenter, has 4 different groups. Yeah. Right? So it says identify all the, sorry. So chiral center is a stereocenter. Chiral centers have 4 different groups. But cis and trans, okay, that's a stereocenter, but it's not a chiral center. And you can't, from a cis and trans, make a non-superimposable mirror image. But they're different molecules for sure. So for example, it's like cis would be, and you try to make a non-superimposable mirror image, we make the mirror image of that, it's superimposable, right? It's not a chiral center. Chirality has a very important influence on the properties of molecules. Okay? Cis and trans molecules always have the same, cis and trans always have a different set of physical properties. Chiral molecules almost entirely have the same physical chemical properties. They're just mirror images of each other. Okay? So it turns out the properties ends up being exactly the same, except when they interact with other chiral molecules. B?
Yeah, did you say it had a stereocenter?
Oh, yeah, it has a stereocenter. It's these two, but those are chiral stereocenters. So a stereocenter, right, means that you can have different spatial arrangements of atoms. That's all it means. So cis and trans are stereocenters. Okay, but chiral molecules also have stereocenters because you can make different spatial arrangements on those chiral atoms. So stereocenter is the more generic term. Okay, includes cis and trans. Okay, it includes chiral centers. Chiral centers are different in that you have one atom with 4 different groups on it that allows you to build like different stereoisomers. So start with stereocenter, big one, right? Then underneath stereocenters, there's cis and trans, and there's chiral centers. Okay. It's definitions. Yeah. All right. All right. We already did this part, but we'll go ahead and draw the enantiomer. So this is implying a mirror plane. This is how we do it all the time. We just dashed line. And we draw a box over here. So fill in the box. And we want to make the mirror image. So you literally start and draw backwards from the other image. Now, what am I going to do with the CL? Is it going to be forward or back? It's got to look, to be a mirror image, it's got to look exactly like the molecule on the left, just in reverse. Okay, that doesn't mean take the stuff in the front and throw it to the back, because this is a common error. It's still going to look like that. And then CL. So when you do this mirror image thing, where you're drawing the mirror plane, you literally draw the molecule backwards. And that's the enantiomer. Okay? Of course, you could have done that other ways. You could have filled in, like you could have put the ethyl where the methyl is and that kind of stuff. But when we ask for the mirror image, that's the mirror image. Okay. What's the relationship between these two molecules? And by the way, that one on the left is spearmint and the one on the right is caraway. Right? They're enantiomers of each other. They have a double bond over here. That double bond can't be rotated. It can't be cis or trans. And it's the same here, right? So these are enantiomers of each other, the mirror images of each other. Okay. So I have this pair of enantiomers, and if you were to name these, you would just simply go, these are alkyl halides. The chlorine gets the chloro name. Oops. You would number the chain 1, 2, 3, 4, and you would say that it's 2-chloro. And then butane. But both these molecules would be called 2-chlorobutane. So it's not good because, right, we had cis and trans for cis and trans isomerism. We need to have something for this, and it turns out there's this set of rules made up by these three guys, Kahn, Engel, and Prelog. So we often refer to it as CIP notation. All right, sort of sounds like, what is that from the Men in Black? MIB instead of CIP. I don't know, Kahn, Engel, Prelog. I just imagine them with the dark sunglasses and the dark suits. They're laying down their rules. But anyways, we use either R or S. Now, R stands for right, or rectus, actually. And S stands for sinister, which is the Latin for left. I know, huh? Who's left-handed here? Yeah, we don't trust you anymore. But yeah, my wife is left-handed, so I often refer to her as my sinister partner. No, I just made that up. I don't really call her my sinister partner. I should, though. See what she says. So these are the rules, okay? You take the atoms that are on the chiral center, and you rank them by atomic number, and one goes to the atom with the highest atomic number. So that's pretty simple. You just look at the periodic table and you say, oh, hydrogen, 1, right? That's the lowest you can get, except for a pair of electrons, because a pair of electrons can be a group too. So the lowest priority is always going to be hydrogen unless there's a pair of electrons. Then it's the pair of electrons. Higher priority just goes by atomic number. So if you had a chlorine and an oxygen, right, chlorine would be higher priority, right? Oxygen would be a lower priority. Okay, so then what you do is you give the priorities so that 1 goes to the atom with the highest atomic number, and 4 goes to the lowest. And then what you do is you hold the lowest priority away from you. So you have to visually, right, or on paper, switch groups so that the number 4 group is sitting in the back of the plane. So if it was like a molecule like this, and this is actually hydrogen, it was a molecule like this, and I was looking at it like that, in order to orient the molecule to assign the CIP designation, I'd have to rotate it like this, so that this group was in the back, okay? So what that means in all practical terms is that if you have something that's chiral and it has a hydrogen on it, because it won't have 2, right? It'll only have 1 hydrogen. Then what you'll end up doing to assign the notation is making sure that if you drew it like that, that's where the hydrogen is. Or if you drew it like that and you had a pair of electrons, you'd put that back there, okay? So you're always putting it in the back. And then what you do is you take the groups that are facing you and you determine whether the progression of highest to lowest of the remaining groups is going in a clockwise direction or counterclockwise direction. So if I was looking at this one as 1, 2, and 3, right? The progression is going like this, and that's R. Okay. On the other hand, if it was 1, 2, and 3, then it would be this way, and then it would be S, because it's a counterclockwise turn. Okay. So I always tell students, think of it like this. Let's say it's like that, okay? So I have literally all the way in the back, that's 4, and I'm not looking at it. So let's say it's 1, 2, and 3, and then make a circle like this. Which way is that turning? Clockwise, right? If that was your car and you turned the wheel, which way would you go? Say right, please. Yes, you'd be going to the right. So when you're looking at it and 1, 2, 3 is turning to the right, it's R. If it's turning to the left, it's S. Okay.
When you write R, the loop also goes clockwise.
Ooh, the loop on R goes clockwise. Whoa. I didn't even think of that. Do you get that on the R? R goes clockwise.
It depends how you write it.
That's true.
Oh, hush. He had his moment. It's true, though. Capital R, does anybody write a capital R? Because to do that, I'm just thinking you would have to go like this. Does anybody do that? If you do, I don't want to talk to you. So, you don't exist in my world. Yeah, clockwise is R, counterclockwise is S. So if you think about a car, it's right and left, right? All right. So here's an example. Fill in any implicit hydrogens. That's the first thing that you should do because sometimes people forget to draw the hydrogen in. Implicit hydrogen is those hydrogens that we don't draw and we tell you never have to draw, blah, 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 blah. If you're going to do RS designation, it helps. When you're starting, go ahead and write it. Okay? Especially if there's a lone pair that's part of this process, because the lone pair should always be in the back. And if you have a hydrogen and a lone pair and you haven't written the hydrogen, then you're going to be really confused when you do this. Okay, so just be careful. Just write in any hydrogens and lone pairs on the chiral center. Okay, and then we rank the atoms by atomic number. So chlorine got the 1, right? Oxygen got the 2, and carbon got the 3, and hydrogen got the 4. And now we're going to assign R and S, but what's wrong? H is in the front, right? Now I'm going to teach you 2 ways to deal with this. One is just to redraw the molecule. Okay? So if you're going to redraw the molecule, oops. And this takes time, right? If you're going to redraw that molecule, you have to draw the enantiomer. So you could draw the mirror image, okay? Well, actually, I'm going to teach you 3 ways to do it. To redraw the molecule, you have to switch bonds. Okay, how many pairs of bonds do you have to switch? 2 pairs of bonds, right? So you could do that. So if you wanted to do that, you could do, again, you draw the molecule in the same way, that part of the molecule in the same way, but then you switch the group. So on the right, I'd have that, and on the left, I'd have this, O and this. And then at the top, I'd have 1 and 4. That is actually just the mirror image of the molecule. So I drew the mirror image. Okay? And now, my priorities go, oh, that's an H, not a 4, sorry. My priorities go, and this is a CL, I don't know what happened. Nope, that was, I did it wrong, hang on. So I have CL and I have H like that. So now I have 1, 2, 3. Well, what did I do? No, I had it right the first time. All right, stop me before I hurt myself. There's a CL here and an H here. So now I have 4 in the back. This is 1, this is 2, and this is 3, so it's going this way. So it's what? S. So that's one way to do it. The other way to do it is this. The hydrogen's in the front, right? It's going like that. That looks like R. This is like the most expedient way. But H is, let me do this. I'm actually not going to say H because it's not always an H. 4 is in front. That didn't show up so well. So what does that mean it is? It's actually S. Okay, I'm going to teach you another way. That makes sense though? You just assign it, you say, oh, it's in the wrong place. Right? Now, if you're asked to draw a molecule, you still have to know all those tricks, right? Okay, so 1. Oh, actually, how do I want to do this? It doesn't really matter how I do it. So, yeah, I'll do this. 1, 2, 3, 4. 1, 2, 3, and 4. So I had to bring a Sharpie to class. I just wrote it on my hands. I wrote the numbers 1, 2, 3, 4. Okay? So the way this molecule is oriented right now, right? It's 1, 2. So I put the 1 and 2 on these fingers. The 3 is automatically my thumb, right? And you don't have to, how to say this? You don't have to write these in any order, but you notice what I did? I wrote them opposite of each other. So you could put the 1 on your thumb and the 2 on your here and 3 here if you want to. But I find these are the easiest 2 fingers to place on a piece of paper. Right? So I just go 1, 2, 3. You notice I have the 4 on the back of my hand? Why don't you put the 4 on the back of my hand? Because it's in the front. And 1 and 2 go like that. So when I look at my fingers, it goes like this. It's S. And you'll find that that is actually a really useful way to do it. Now, why didn't I use this hand? Because 1 and 2 don't match. Like I do 1 and 2, I can't get 1 and 2 on the paper to match with the 4 in the front. Right? On the other hand, if it's already in the back, it turns out then I can do something. Turns out, if you do it the same way all the time, as soon as you're able to match your fingers onto the paper, you'll know what the configuration is based on whether it's your right or left hand. But again, it's not hard to just assign it on paper.
But then you have to remember which hand to touch.
Yeah, I know, because this is the S. Sorry. Okay. So that was the other way. Once we did this, they're talking about rotating it. Most of the time we don't, for assigning R and S, we don't rotate it. We just look at it and then we and we just assign it. Okay, so anyways, I think I'm out of time today. So